From this lecture, we are going to start a new module. This module will be based on what is called feedback. And here we will not discuss a new type of circuit. Rather, we will discuss a technique, this feedback technique, which is applied on circuit. And we will see that it has various consequences. Majority of the consequences on the performance of original circuit are desirable, but there will be one or two consequences which we do not want. So we can say that that is the price we pay for the various other positive effects that arises because of this feedback. So we are going to study this feedback technique in amplifiers, because this is one of the most important circuits that we used in electronics. So this feedback word is very common and very technical also, and it is not confined only to amplifiers, not even only to electrical engineering. In fact, this phenomena, the phenomena of feedback, is very widely prevalent, and it occurs in various domains of the nature. And it has been found that when it is applied to amplifier, it has many desirable properties, of course, at the cost of certain degradation in some of the other properties. And this feedback technique has evolved into a very vast knowledge area. And typically, this is covered in a very rigorous way, in a very mathematical fashion, in control theory, which typically is taught in higher semesters. So in this course, we will focus mostly on the qualitative aspect of this feedback phenomena, and somewhere we will try to be more technical and try to use some maths also. But here we will just try to get the flavor that what is this feedback and what it does to a circuit. In fact, we have already encountered this feedback in not only in oscillator, but even in inverting and non-inverting amplifier configuration of an op-amp. So definition of this feedback is that we take a part of output, say for example a fraction of output voltage, and it is then applied back to the input. In addition to some external input also might be there. In fact, very often it will be there. So this is the meaning of feedback, and it has two major categories, that is called positive feedback and negative feedback. So today let us just accept or claim that this positive feedback actually occurs whenever this the output fraction is added to the external input, and whenever this output is subtracted from the external input, we have negative feedback. So in terms of maths, this is one of the ways in which you can figure out whether we have positive feedback or negative feedback. And these two types of feedbacks, they will have different consequences on the behavior of the circuit, that means the output. So that is why we distinguish them, and in future classes we will see a different way of figuring out what is the polarity of the feedback, because using this definition, that means when it is external this applied signal gets added or subtracted from the external, then we have the suitable polarity. This definition might not be so easy to apply in various circuits. So we will see different technique of finding out this polarity. So now we will try to list all the, or rather number of consequences of this feedback. So we will now list effects of feedback, and then one by one we will study them. Some of the things we will study in quite general way, some of them we will study by taking specific example. So as I pointed out, it has a very wide impact on the performance, and we are going to talk about only some of them. So first is, change the color to first effect is gain desensitization. Second is bandwidth extension. Third, we will list later on because that is undesirable effect. Fourth is linearity improvement. Fifth is modification of input and output impedances of the amplifier. And sixth is stability improvement. So now let me come back to the third one. So third is gain reduction. So here I have mentioned only 6 out of many changes that occur because of the feedback. Out of these, all the points except the third one mentioned in green, they are all desirable. We will see that all these changes that occur because of feedback in an amplifier are desirable. Only this third one is undesirable. And you can say this is maybe the price that we are paying for all these advantages. And out of all these things, in today's lecture, we will talk about quantities up to these 1, 2, 3, 4, 5. 6 part we will not discuss. But here, stability improvement means we saw that in the last class, if we have a bandpass filter, silent key bandpass filter, and if you take inner gain G is equal to 3, then it starts oscillating. So we say that it has become unstable. That means the nature of the circuit changes. So that is what we mean by stability. And usually the amplifier will also tend to behave like an oscillator, because you have already seen the feedback model of oscillator fundamentally contains an amplifier. That is the starting point. And we convert that amplifier with the help of a beta network into an oscillator. That means a circuit which gives output without any input. So we say that amplifier has also become unstable when it starts behaving like an oscillator. So whenever we want amplifier not to behave as an oscillator, then this feedback is helpful, and we say that it improves the stability. That means it prevents amplifier from tending to behave like an oscillator. So now what we will do, we will see the general architecture of a feedback network, and then one by one we will discuss all these first 5 effects of the feedback. In fact, we have already seen this architecture in the oscillator. So we saw that there is a block A, and this is amplifier, and then we had a what is called feedback block, and that we had been denoting with parameter beta, and then in general there will be external input as well, and this external input will now get combined with the feedback that is getting produced because of this feedback network. And here we have Y output. So this is input side, this is output side. And here we are mentioning input and output in terms of X and Y, just to keep it general, so that this X and Y, they need not be always voltage, they can be current also. So, uh, so this is going to be the general architecture. And as I pointed out, because of there are two polarities of the feedback. So this XF will either get added with the external input or it will get subtracted from the external input. So based on this, we have the polarity. And then there will be equivalent signal XE, which will be processed by the amplifier to produce Y. So here in this architecture, A, which is amplifier in terms of what it does with the XE, but this is also called feed forward system. And beta is of course the feedback network. And here we have this is called comparator, or maybe adder also. So here, since the feedback quantity, this Y could be either voltage or current. So we will see later on that how we sense or how we tap this output and give to feedback will vary depending upon whether the quantity we are picking from the output is voltage or current, right? So here there will be a different sense technique. So feedback network is sensing this output, and then it is producing this XF output. So here we have few components, the feed forward component, then we have feedback component, then the comparator, and sense mechanism or technique. So once we put this amplifier A into this loop, you can see there is a loop closed path. So the overall transfer function of the circuit will be different from that of the single amplifier. So now we want to define the overall transfer function, and we treat the whole circuit as a single block. So in fact, we have already derived this for the oscillator part by taking this positive sign here. So for positive sign, we found that output by external input will be equal to A divided by 1 minus beta A. So this is what we get when we have a positive sign here. But if you carry out the derivation with the negative sign, then this denominator will become positive. So their plus minus manifest as minus plus in the denominator of this transfer function. And this transfer function we will be calling as AF, the feedback transfer function. So here we say that AF is uh, closed loop gain or the transfer function. And A is called open loop gain. So here we find that whatever may be the polarity of this feedback, this factor, an important factor beta A appears in the denominator. Later on we will see that this factor is very important factor and it will appear again and again uh, in whatever parameter we calculate. The overall gain, for example here, or the input impedance, output impedance, or the bandwidth change will also be actually affected by this factor beta A. And this beta A factor is called loop gain. And XC is sometimes called as error signal, right? So these are the three important terminologies or parameters that we will encounter again and again in the discussion of this feedback. Now let us quickly go back to our well-known amplifier, non-inverting amplifier using op-amp, and try to see that its overall gain is of this form, equation 1 that we have written here. So we give our input to plus terminal of the op amp, and we have two resistors R1, R2, and then we feed from the common point of R1 and R2 here. So here XE error is going to be X minus Y into R2 divided by R1 plus R2. That means X minus XF. And here we know that for this case, the gain uh, as per the equation 1 will be given by A divided by 1 plus this factor beta A, where beta is going to be R2 divided by R1 plus R2. So Y by X is A divided by 1 plus R2 divided by R1 plus R2 into A, right? And this can be written as 1 by A plus R2 by R1 plus R2. And we know that for op amp, A is ideally infinite. Even for real amplifier, this will be of order of at least 10 raised to 5. So we see that Y by X gets approximated to 1 by R2 divided by R1 plus R2. So this will turn out to be 1 plus R1 by R2. And we are familiar with this formula. So we see that we are able to arrive at the gain of this non-inverting amplifier starting from equation 1, which was derived for a general feedback system. So here we find that the signal that is coming from the feedback network is getting subtracted. So that is why we say that we have a negative feedback here. Now let us start discussing the all those five parameters or the consequences that was pointed out in the beginning. So we want to see that how the gain desensitization occurs. So gain desensitization basically means that the overall gain is going to be less sensitive to the change in the gain of the amplifier. So here we have an amplifier. If the gain of this amplifier changes by large amount, then the change in the gain of the overall amplifier is going to be smaller. And actually, let me point out that all those properties or the effect that were pointed out, they were actually pointed out for the case of negative feedback. So here we have our input X and we have output Y, and it has been put into a feedback, negative feedback configuration. So we know that now as a whole, the gain offered by this circuit, the feedback, the closed loop gain is going to be A divided by 1 plus beta A here. So here we can clearly see that gain is of course less than the open loop gain reduction has taken place. But now we want to know that what will be the percentage change in overall gain for given percentage change in the open loop gain of the amplifier. So what is the relation between these two quantities? So we can start from equation 2, we can differentiate it with respect to A. So we try to find out dAF by dA. So if you carry out this differentiation, it will turn out to be 1 by 1 plus beta A whole square. So what we want is, we want this quantity and this quantity, a relation between these two. So we can see that we already have delta AF by delta A. So we need to convert it into percentage form. So we do the manipulation. So we multiply and divide this factor by A. Here. So we see that this first factor is AF, this factor, and what we have here is A and then 1 plus beta A. So we can take this on left hand side and this on right hand side. Right. So this can be approximated to delta AF by AF is equal to delta A by A into 1 by 1 plus beta A. Right. So here you can see that whatever may be the percentage change in delta A, so percentage change in A, that gets divided by factor 1 plus beta A. So obviously the percentage change in AF is going to be less than that of the percentage change in A, open loop gain. So here we can take one example also. That means suppose A is 10 raised power 4, and this is will definitely be the case in real life, and beta is equal to 1 by 10, right? And 10% change occurs in A. So when A, that means op-amp is fabricated. So from one piece to another piece of the op-amp, from one IC of op-amp to another IC, there is a 10% change. So this is due to maybe fabrication error, or maybe this could occur during the operation also for any given op-amp as the temperature changes. So if we are using this op-amp in the usual non-inverting configuration like this, then this A undergoes 10% change, which has 10 raised power 4 value, and this beta network is 1 by 10. So in this case, you can see that percentage change in AF is going to be the percentage change in A divided by 1 plus beta A. So we have 10% change, and 1 plus beta is 1 by 10, A is 10 raised power 4. So this will get approximated to 10% divided by 10 raised power 3. So you can see here that percentage change that occurs in AF is going to be very small compared with that of A. So this is the advantage of a negative feedback. Now let us talk about the second consequence, that was the effect on the bandwidth. And it was pointed out that bandwidth will get extended. That means feedback amplifier will have more bandwidth compared with the uh, standalone or the open loop amplifier. So for this case, we will have to assume a transfer function for the amplifier A. So let us say that we have amplifier A, which is of one pole type. That means its transfer function is like this. So here you can see that this is of type low pass. So if you do the Bode plot, we know that it is going to be like this. Yeah. So A naught is the DC gain, and the gain reduces as the frequency increases. So here the bandwidth is from DC to omega h. So omega h is minus 3 dB cutoff frequency. That means after this there will be large decay, and up to this point the gain would have reduced by minus 3 dB. That means amplitude would have reduced by 1 by square root 2. So now we want to put such an amplifier, this type of amplifier, into negative feedback, and then we want to know that what will be the bandwidth of the overall amplifier. So we take this amplifier, we put into negative feedback like this. This is A, this is beta. And then we want to know that as a overall, what will be the bandwidth. So we know that AF is going to be given by A divided by 1 plus beta A. And the transfer function for A is A naught divided by 1 plus S by omega H. Similarly here 1 plus beta A naught divided by 1 plus S by omega H. So this is the transfer function of the overall amplifier with the feedback. So this can be simplified to 1 plus S by omega H plus beta E. Right. So this we can rewrite as A naught divided by 1 plus beta A plus S by omega H. Right. So now we can divide it by factor 1 plus beta A. So this becomes A naught divided by 1 plus beta A 1 plus S by omega H into 1 plus beta A. Right. So now here we can see that we have now a pole at omega H into 1 plus beta A. And keep in mind 1 plus beta A is always greater than 1. In fact, it will be very large if A itself is very large, which happens in the real life or op-amp based circuit. Right. So what we see now is that if we earlier had this type of response, this was omega H. So now you can see that pole is at a location here, omega H into 1 plus beta A. Right. So this is also nu minus 3 dB cutoff frequency or minus 3 dB point. But here you can see another effect which was pointed out in the point 3 and that is undesirable, and that effect is here. The DC gain has now reduced from A naught to A naught by 1 plus beta A. Here we have taken low pass type, so this is the DC gain reduction, and the gain is now A naught divided by 1 plus beta A. So you can say that this factor 1 plus beta A, this is the factor by which bandwidth has increased, but this is also the factor by which gain has reduced. So now what we will have is Bode plot, which will be like this. So this is new DC gain and this is the original DC gain. Right. So this is the A or maybe AF. So we see that now bandwidth is more. Omega H into 1 plus beta A. So bandwidth has increased, but of course at the cost of the reduction in the DC gain. Right. So this was with the help of one low pass type of amplifier. But what if we have amplifier whose transfer function is of high pass type? So we can take that also. So this is for the low pass type of amplifier. Now if you take a high pass, then also the conclusion remains same. So in this case, our transfer function of the amplifier will be given by this expression. Right, so here A naught is gain at infinity. Right, so this is gain at infinity, and then we have 0 at origin, and we have a pole at omega L, and the transfer function you can see now is going to be given by this plot. So this is the band over which this amplifier cannot be used, and it can be used beyond omega L. So now if you want to increase the bandwidth, then this omega L should be reduced. That would be the meaning of enhancement of the bandwidth of this type of amplifier. So now in negative feedback, if you put this amplifier in negative feedback, the overall gain is going to be given by this transfer function. So this is the transfer function of the feedback amplifier. So here you can see that now we have gain, which is A naught divided by 1 plus beta A naught. So we see that gain has reduced, but now what will be pole location? So we can rewrite this as A naught divided by 1 plus beta A naught omega L divided by 1 plus beta A naught plus S. So here we can see clearly new pole at omega L divided by 1 plus beta A naught. So here what we will now have, this was the original amplifier. Now when we put this amplifier in feedback, then what we get is this response. So this is AF, and earlier we had A. So here you can see that now it can be used over a wider band. So now the band over which it cannot be used has reduced from this much to only this much. And again, all these changes, they are getting affected by factor 1 plus beta A naught. Similarly, for the bandpass type of amplifier also, the same phenomena occurs, but I will just point it out that if we had this kind of bandpass amplifier A, then if you put this amplifier into negative feedback, its new response is going to be like this. That means gain will get reduced and bandwidth will get increased. Now we will talk about linearity improvement. So what do we mean by first linearity is that we want output to be of this form for larger and larger x. So this is the format, and ideally we want this should be valid for more and more x. That means the input. So suppose we have the amplifier, single op amp. So it typically has a large gain. So in fact we will have this kind of response, and very quickly it will reach to the what is called saturation. That means it will reach to the value of plus minus 15, which is the DC supply voltage given to op amp. So here we will see that output becomes saturated VO max for an input which will be typically very small, right? So this is the performance of amplifier A. Now if you put this amplifier into a negative feedback, then we know that its gain AF is going to be given by A divided by 1 plus beta A. So this is clearly less than A. In fact, it will be significantly smaller than A because this factor A is very large. Beta will be not so large usually. So what will happen to new output and input relation is that it will be now like this. So since the gain or the slope is now smaller, so now the output y is AF into x. Earlier the output is y is equal to A into x. So here we see that it again saturates, but now for an input Vi2, and this Vi2 will be typically very large compared with the original input. So that means now this can be used for to handle larger input voltages. So it can amplify larger input voltages before the distortion occurs. So this is one meaning of linearity improvement. Second is we can consider a composite amplifier. That means we have a scenario where there are two gain available based upon the input range. So this is output, this is input, and suppose amplifier initially offers large gain and then this type of gain before it saturates. So here what we wanted ideally is, keep in mind that we always want a straight line kind of response from an amplifier. So what we always want is y is equal to mx kind of behavior, which is not here. So now we have an amplifier which has say gain A1 over this range of the input, and then gain A2 over this range, and then of course zero gain, that means saturation. So now if we put this amplifier in a negative feedback, then we know that we are going to get AF1 equal to A1 divided by 1 plus beta A1, and A2F, which will be A2 divided by 1 plus beta A2. So what will happen is now the plot will get modified to something like this. That means we will have a response like this and this. So we still have a transition here at this location, but now you can see that this plot is closer to a straight line than the previous one. So this is another meaning of linearity improvement. That means if the amplifier has variable gain over the input range before it hits the ceiling, of the maximum value, then the amplifier gain will get made more closer towards the constant value over the entire range. So now you can see that over this entire range, it has a more straight line or a constant gain over this range. So this is for the step type of response. But in general, we know that we will have a amplifier which will give this kind of amplification response. So even for this case, when we put this into a negative feedback, its response will get modified to this one. So here also you can see that the response is now more like a y is equal to mx for wider input range. So this is the meaning of enhancement of the linearity range. Now we come to effect on the input and output impedances. Z in and Z out. So there I mentioned Z in and Z out modification, but I am here mentioning improvement because we will see that this is indeed an improvement. So this changes occur in the desirable direction. And this in today's class we will see with the help of one specific example, but later on we will study this phenomena in a most general fashion. So what we are going to do is we are going to take a common gate amplifier and then we will try to put it into feedback and then see that after feedback what is the input and output impedance of this common gate amplifier. And we will notice that all these changes they occur in a desirable way or in the desirable direction. So here we have common gate amplifier. So here we have a common gate amplifier and we know that for lambda is equal to 0, the gain is GMRD and Z in is 1 by GM, Z out is RD. So we know that this value is low. And here what we are doing is we are using as a voltage amplifier. We have a input voltage Vi that we want to amplify and appear as Vo, right? So we have already seen that if the source has certain internal impedance, then it is better to use an amplifier with large input impedance, right? And on the output side, we have this output voltage. So on the output side, we should have low output impedance uh, because it is going to act like a or rather we are going to use it as a voltage source. So the output impedance here, Z out, should be low. But unfortunately, what here we have is an unfavorable condition. Z in is low and this is desired to be high and output is RD. So of course, only when we make RD low, then we can make output impedance also low. But if you try to do this, you will lose the gain also. So you cannot reduce RD to make Z out low, right? So we want gain also to be uh, decent value. So now let us try to put this into a negative feedback and see that how these impedances they get modified. So we take resistive divider circuit to create the feedback. So we have connected output to this R1, R2 feedback network and then we are feeding to the gate, right? So we have created this feedback amplifier. Now in this amplifier, we want to know that what will be the uh, new gain. So we have created this feedback amplifier. Now in this amplifier, we want to know that what will be the new gain. So we have created this feedback amplifier. Now in this amplifier, we want to know that what will be the new gain. So we have created this feedback amplifier. Now in this amplifier, we want to know that what will be the new gain. new input impedance and new output impedance. So here the feedback is PF is equal to R2 by R1 plus R2 into VO. That means beta is, which is VF by VO, is equal to R2 by R1 plus R2. So this is the amount of feedback we are giving. And here the feedback polarity is negative. That we will not explain here. So we have put this amplifier into feedback, and we want to know that what will be the overall gain. So overall gain is always given by this formula. So here gain is going to be GM RD divided by 1 plus R2 by R1 plus R2 into GMRD. Now let us try to see that what will be the input and output impedances. So for that we will have to draw the small signal equivalent circuit of this amplifier with lambda is equal to 0 and then do the calculation. So let us do that. So here we have our MOS, and it is being fed by the feedback network, which is connected to output, which is drain here, and then we have RD here. And for finding the input impedance, this is what we will have to do. So we connect here Vx, and we then try to find out Ix. So here we have Vg, this is Vs. So if we apply KCL at source, we get Ix is equal to minus Gm Vgs. So this is minus Vg, Vs is Vx, and Vg you can see is R2 by R1 plus R2 into this VO, or this can also be written as beta into VO. So Ix is equal to minus Gm beta VO minus Vx. But we have already found out AF to be equal to VO by Vx equal to E of the common gate divided by 1 plus beta A, which was Gm RD divided by 1 plus beta Gm RD. So from here we can find out VO and substitute in this equation, say 3. So Ix will become equal to minus Gm beta GMRD divided by 1 plus beta GMRD Vx minus Vx. So this will become finally Gm Vx divided by 1 plus beta Gm RD. So we see that Vx by Ix is 1 plus beta GMRD divided by Gm. So we see that the new output impedance with feedback is equal to 1 by Gm into 1 plus beta, and this GMRD is the original gain. So here we can see that we have this is Z in 1 plus beta A. So we see that the input impedance now becomes larger, and this is what is desired from a voltage amplifier. It should have large input impedance so that it can handle non-ideal sources more easily, input sources. Right. So again, we see that this factor beta A appears here. So this loop gain is very important factor. It appears everywhere. In fact, in a form of 1 plus beta A. Now we try to find out Z out with feedback. So we again draw the small signal model, but this time source is going to be grounded because this time the model is going to be this for finding out output impedance. So here we have feedback. So in this case, we see that we will have to put our unknown source here, Vx. So we see that this Ix will get splitted into three parts: IR, Ig, and this I feedback. So you can see that this scenario is equivalent to three impedances in parallel. So this one is Rd, this is R1 plus R2, right? So these two impedances are known. We just need to find what is the impedance here because of the MOS, this one, right? So we see that Ig is equal to Gm VGS, and since source is 0, so this is Gm into Vg, right? And Gm, this Vg is feedback, so this is beta into Vx Ig. So that is why the Zg, this impedance, is equal to Vx by Ig, and this is equal to 1 by beta Gm, right? So here what we do is that we try to take this R1, R2 very large, very large compared with Rd, right? So here we see that the impedance offered by MOS is this one, and this factor is going to be typically small. Gm is already small, beta is also small. So we see that the overall admittance that we will see here is going to be parallel of admittances of all those three uh, impedances. So here this is one, so this ZF is impedance of this path, this is impedance of RD, and this is impedance of ZG is impedance of MOS. So this we have already calculated to be equal to right. So this is a small, this is also going to be moderate, but because R1 plus R2 is very large, so this is going to be smallest out of these two. So we can make an approximation and we can write here like this. So this is Y out approximately or equal to beta GMRD plus 1 divided by RD. So Z out is going to be approximately equal to RD divided by 1 plus beta GM RD, right? And we have already seen that this is 1 plus beta, this is A. So the output impedance will be given by this factor, and this is smaller than RD, which was the output impedance without feedback. So this is with the feedback. So all these are with feedback. So we see that the output impedance reduces, and this is desirable for voltage amplifier, so that even if you connect various loads, the voltage delivered to it is not going to much affected. So we saw that the five effects that we pointed out of those five, except gain reduction, all are desirable. So that is why negative feedback is quite often preferred.